Humphries from the University of Canterbury in New Zealand, I assume. I'm afraid.
Yeah, you got that one right, yep. You'll be able to pick it from my accent after not so long anyway.
Everyone's such an international traveller nowadays.
I know.
Who will be speaking on the properties of the TBR metric?
Thank you. So I'm studying at Canterbury University, finishing my PhD with Charles Semple. Some time ago, he gave me a paper by, this cord's kind of long, it hangs all over the place, by Yun Song, and in which he explores some ideas in rooted SPR, looking at the idea of some properties of this metric space. And the natural thing for me to do, since I'm interested in enumerative combinatorics, was to take his results and try to upgrade them for unrooted trees, and this is what I'm going to tell you about today. So TBR is an example of a tree rearrangement operation, which, loosely speaking, is you take one tree, you cut it into two parts, and stick it back together. So we've heard about this from Magnus, from Catherine St. John. Other people have talked about it. I don't think anyone's really talked about TBR yet, so this might be a pleasant change for you. These operations were first introduced by David Robinson in 1969 for unrooted trees, and have been extended in a whole lot of ways. The original one was the NNI operation, and it gives you a measure of how similar two trees are. So we're talking binary trees on the same set of taxa, and we want to know how much are two trees alike, really. More in a rooted sense, this will give you a measure of how much hybridization is required within a system to explain incompatibility between a pair or a set of given trees. Useful in that sense also, as we heard from Magnus, it allows you to search through a tree space by starting with a tree, look at all the trees around that point and maybe calculate a statistic, the likelihood, parsimony score, whatever you want to look at. Move to the tree that best improves your score, and you keep doing this until hopefully you find a global optima. Maybe you get stuck in a local optima, but I don't know, I don't really play with algorithms, so I'll leave that to computer scientist people. Yeah, okay. So what do we need here? We need some notation as a mathematician. I've only got one Greek letter in this talk, you'll be happy to know. I don't think I've seen it in any other talks yet, so that'll be a nice change as well. For the set of all trees on vertices, the leaf set 1 to n, we call this, with this curly letter, it is a T. I'm assured it is a T. It looks more like a J here, but that's not a problem. So the three operations that we're interested in are the nearest neighbor interchange, subtree prune regraft, and tree bisection reconnection. Again, Magnus already explained the first two, which is a good thing. You gave me a get out of jail free card on that one because I only have the picture of the TBR operation. Yeah. So pretty much, like I say, you can cut the tree into two parts. Unlike SPR though, you don't preserve the orientation of one part. You don't cut off a rooted subtree and regraft that. You can rearrange the two parts in any way you like. So here you've got an example. You cut the middle edge in this 6-leaf tree and then rejoin it with an edge connecting the pendant edges adjacent to 2 and 5 instead. This is actually the simplest example of a TBR operation which is not an SPR, which you can see easily that any 2-leaf tree you cut off, you can't change its orientation, so we need at least 6 leaves. Nice thing about all of these operations is that they do induce a metric space on Tn, so there's nice properties to this. And what I'm interested in today is, given a tree, how many different trees can you reach by performing one single operation? So we're looking at how quickly you can cover the space of trees with using one of these algorithmic searches, essentially. So, borrowing more topological notation, we're going to talk about unit neighborhoods. Got this definition. So, a unit neighborhood of a tree T is every possible tree in the space you can reach by one single TBR operation. And you can use this definition for NNI or SPR as well. Exactly the same definition, just a different subscript. For both NNI, this is already, and SPR, this is already known. And it doesn't matter on what the shape of the tree is, which is, for NNI, that's not surprising. For SPR, it might be a wee bit more surprising. The sizes of these have been known, I think it was in Allen and Steele, the SPR size was given. But for TBR, the size of this neighbourhood does depend on the shape of your tree. It's not purely dependent on the number of leaves. It's a wee bit more complicated than that. So current known bounds, we've got a lower bound and an upper bound. Quadratic lower bound on the left here is actually the exact size of the SPR unit neighbourhood. The fact that that would be a lower bound follows from the fact that every SPR move is also a TBR move. The upper bound is cubic. So we've got quadratic to a cubic range of values possible. But neither of these are sharp, which is where there's a wee bit of room for improvement. So yeah, here we go with the cool maths equations. So what I did was came up with this recursion formula, which you can use for any unrooted tree to figure out the exact size of the unit neighbourhood. So the picture we're interested in here is the one at the only one you can see now. Was going to be the one at the top, but you take an unrooted tree, and you can always find a cherry. In this case, I've called XY, and we're just going to do an induction around that cherry. So how many ways, what can you do to this tree to do a TBR move? The first option is to do a move that keeps the cherry there, that keeps XY in your output tree, which is equivalent to deleting that leaf X, doing a TBR move, and adding X back in. So that's where we get this first term in the recursion, which you actually can't see now, because evidently red and blue don't go very well together. So there you go. It's the neighbourhood of T without X. The next thing you could do, I'm going to have to change from red next time I do this. The next thing you can do is cut off either X or Y and graft it onto some other edge of the tree so that XY is no longer a cherry. So in the case of, if we do X first, we can cut X off from U here and graft it to any edge not adjacent to you, not incident with you, sorry. If we graft it on there, then you still have XY as a cherry. So that gives you 2n minus 6 possibilities. There's 2n minus 3 edges in the full tree, 2n minus 6 once you get rid of the 3 edges here incident with U. You can do the same thing with Y, but when you do that, you can't attach it to any edge adjacent to U or V. If you attach it to some edge adjacent to V, you'd get another tree that you already got when you did this with X. So that's 2n minus 8 possibilities, so you get this 4n minus 14, which you can see there when I flick back a slide. And the last part is conceptually the most difficult. This is where you cut off a proper subtree of the remaining part. So not an entire part of R1 or R2. Again, that would be covered by one of the previous two options, but you take a proper subtree of either R1 or of R2 and regraft it to either X or to Y. So that's where you get this cool, funky Greek letter. This function here counts how many ways, given a rooted tree, how many ways can you cut a proper subtree from it and choose a new root for that subtree. So here's an example. We have a rooted tree there. We want to, because we're doing TBR operations, remember the orientation of what you are going to regraft onto the tree matters. So we cut off this proper subtree, 3, 4, 5, and unroot it, because we can attach it any way we want, and then we choose a new root, and I've chosen to root it on this edge, the pendant edge that attaches 4 to the tree. So this is one example of one of these operations counted by the xi function, and we just want to count how many of these there are for every rooted tree. And when we do that, you get this recursion formula. So there you go, there's a recursion formula. Trouble is, we don't know how to calculate this function here. Oh, sorry, the factor of 2 in front is from the fact that you can graft either to x or to y. Oh, yeah, so there you go, on the picture that is no longer up there. So, next problem is calculating this thing here, which is easier in a way, and I've got another picture for you. I actually drew this one this morning because I realized that I'd left out the hardest part of the talk, and I was going to make you just try to imagine it in your head. So the last picture we're interested in is the bottom one here. Given a rooted tree, how can you calculate this function? Again, you get a recursion. We delete the root to get 2 other rooted trees, and you have 2 options then for how you can cut off one of these rooted trees and choose a root on it. You can either cut all of R1 or all of R2 and root that. The number of ways to root that is the number of edges in the tree. Almost, it's number of edges minus 1, because when you cut it off you have a rooted tree, so you have to suppress the root. So for each of those you get this minus 1, which you can't see, becomes a minus 2 when you add up over the 2 trees. The other option is to cut a proper subtree of R1, R2, and that's where you get this recursion down to the next level. So you can work out that recursion, and that's fine. And using this with the previous one, you can actually calculate for any tree the size of the TBR unit neighbourhood. So that's it, except that you've got, oh, and there's upper and lower bounds which are sharp on this thing, which will be useful soon. But it's a nasty recursion, and it's not really any more helpful than taking a tree, doing all your TBR operations and counting the size of your output, because you have to do so much recursion to do this. So the obvious thing to do, I guess, since I'm interested in how big and how small this neighbourhood can be, is to look at the upper and lower bounds on psi function, apply that to the previous recursion, and hopefully we'll get something useful out of it. The nasty thing is when you get this here, and like I say, both these bounds are sharp, but it doesn't look very nice at all, that lower bound. So we'll start with the good news anyway. Good news being this theorem here. So this is the sharp upper bound, tight upper bound for the size of the TBR unit neighbourhood. It's still cubic, same as the previous known upper bound. However, I've also characterized which trees this holds for. You get equality only for caterpillar trees. Going back to Yun Song's work, this is interesting because he actually showed that for the analogous case for rooted trees, which is rooted SPR, caterpillars actually minimize the size of the unit neighborhood. So there's a dichotomy there which I don't know how to explain. It's interesting, and I guess leads to this idea that perhaps the lower bound may be given for balanced trees, since that's also what Song showed. This I don't know about. I haven't actually conjectured it because I only have one neck and I don't want to put it on a chopping block yet. Bad news. This is the function that gives you the lower bound. So if you have a look at that for a while, you'll see that you've got a double sum of floors of log base 2, which in anyone's terms isn't any fun at all to work with. But it is a lower bound. Again, it uses this induction from the top picture, except you choose xy to be a cherry that's at the end of a longest path, in which case you can assume R1 or R2 contains at most 2 leaves. Otherwise, you'd have a longer path going through there, and that's the best I've managed to get so far for the lower bound. There are ways in which you can get a better one, assuming that your tree has a certain number of leaves, but it just gets messy. Messier than this, believe it or not. And this is a strict improvement on the given quadratic lower bound or the size of the SPR unit neighborhood. For all n larger than 9, it does give you a slightly larger size. How much larger, though, is a question of interest. Is this still quadratic? Having a brief look at that, it's hard to see whether it is quadratic or if it's bigger than quadratic. We know it's not bigger than cubic because otherwise we've got a lower bound bigger than our upper bound, and that's a little bit contradictory. I guess it would invalidate all that I've said if that happened. So just briefly, a quick look at the asymptotics here. If we take the function from this previous theorem I just had on the last slide, then you can derive from that this generating function, which is a little bit prettier, I guess, easier to see what's going on. So by generating function, I just mean if you take the coefficient of x to the power of n in there, then that gives you a lower bound on the TBR neighborhood for trees with n leaves. It does look a little bit prettier, but this final term here is still a problem because you've got, you're taking this product, the convolution of two generating functions, one of which is x squared plus x to the 4 plus x to the 8 plus x to the 16. There's no way to play with that nicely that I've found as yet. So I guess as far as anything else that goes, the first thing to do is figure out what happens to that asymptotically, to this, either the generating function or the lower bound that I gave. I had a brief look at this with Stefan a couple of weeks ago, and it looks as though that is n squared log n. So it's bigger than quadratic, smaller than cubic. I've also calculated the exact lower bound for some trees, and using that lower bound calculated up to about n equals 500, plotted them on a log-log graph, and it looks to lie between the cubic and the quadratic. So I think n squared log n is probably what you'd find that would do asymptotically. But it's not a tight bound. I know that it's not a tight bound. I think that as you get to bigger and bigger n, then the gap between the actual tight bound and the bound I've just stated increases quite dramatically. So it'd be nice to be able to find the tight bound, characterize the trees. Whether that's possible, I don't know. And ultimately find a closed form. Given a tree, find some expression that gives a closed form. What I showed you today was this top formula, which is nasty because you have a recursion, but within it you've got another recursion. Yun Song's formula for rooted SPR, I've given at the bottom here, doesn't have any recursion in it. It just has this sum over a gamma function, which for unrooted trees, Song defined as the distance from an interior vertex back to the root. Taking this concept and putting it into unrooted trees, you have no point of reference. You have no root to measure the distances to. So how one would go about taking this and putting it in an unrooted setting, I don't know. And that's about it. That's where I'm going to leave things.
Do we have any questions?
You think that maybe you can get a better bound if you assume some properties on the tree, and you not just try to get as a function of n, but as some other properties like diameter or depth or things like that?
Possibly. Assuming a property on the diameter is essentially the same as looking at the balance of the tree, which is, this is the idea of Song. He had the caterpillars minimize it for rooted SPR, and the balance trees maximize the size of the neighborhood. So maybe that would be one way of looking at it, by restricting the diameter of a tree.
Maybe for some trees it is cubic, and for some trees it is quadratic. I mean, it doesn't.
This is true. Yeah, it's not something that I've looked at. Something I didn't mention is that the problem with getting this lower bound is when you do the inductive step, the structure of your two subtrees R1 and R2 is changing. And I think when you restrict the diameter, you'd get the same problem. each time you do an inductive step, you actually may be jumping to the other side of the tree to pick a cherry, and it just gets out of hand. Yeah.
Any more? Yes.
So you didn't quite conjecture that the balanced ones were going to be the...
I didn't quite, but I almost
but
did.
how do they grow then? Do you know the...
No, I haven't played. It's the same problem as with the structure of these two subtrees changing. The structure of R1 and R2 is crucial to the size of this neighborhood. Sorry?
You don't know how big they're
No. And just another comment on that. Song's proof actually isn't that balanced trees characterize the trees with the maximum size neighborhood. It's what he calls gamma exponential. So they're essentially balanced. They just obviously have to minimize this function, minimize the sum of the distances back to the root. Balanced trees satisfy that, but there's a whole lot of other trees that also satisfy that. So this is again why I wouldn't want to make that conjecture, because I don't have any concept of the analogy for gamma exponential trees to an unrooted space.
Let us thank our last speaker and all the speakers this morning, and I believe the ringing bell means there's coffee and tea outside.
Coffee,